This is my first presentation in person in almost 2 years, so forgive me if I make any mistakes. But thanks again for having me. Today I'm going to talk to you a little bit about categorical data analysis and interpretations for those data. You know, as a statistician in graduate school, they had whole courses on these topics, and you're getting about 50 minutes of it today. So I'm trying to hit the high points, but if you have more questions after this, of course, feel free to speak to me, anybody in my group, and we'll be happy to elaborate. So we'll start with the definition, and this definition is germane to categorical data. So categorical variable is a measure that consists of a set of categories. That seems obvious, but many times when folks come to me for help, they often provide me numbers. Categorical data analysis is kind of its own animal, and the methods that you deal with categorical data are pretty different. Some examples may be a Likert scale, maybe attitudes towards a proposal. You know, you strongly approve it, neutral, and so forth. Another one may be results from a cancer screen. Could be normal, benign, likely benign, and so forth. You kind of see in the data I just presented there that there's maybe some data types that are important. The three big data types for categorical data. The first is ordinal. So this is when the categories themselves have some underlying order to them. The second is nominal. An example of nominal will be the two examples I had above, right? So or at least one of them, excuse me. So the results for the cancer screen may be nominal in some way, although technically you may be able to order that. And then the attitudes for the proposal would be ordinal. The last option would be dichotomous or binary variables. And honestly, a lot of clinical research, we see more dichotomous and binary data, especially as outcomes, than we do ordinal and nominal. But these are the three big data types that we see in categorical data analysis and the types of projects that fellows bring to us. So I want to do a little bit of an exercise so we can, get people talking a little bit. So I present some examples here, and I want to go down the page and see if you know what kind of data they would be. Remember, the three data types are ordinal, nominal, and binary. So what do we think about age group? Would that be ordinal, nominal, or binary? Any idea? I feel like I'm leaning over. Heard it over there. I think she's cheating because she's a statistician, but yes, it's ordinal. What about birth gender? What's that? It's binary. It can also be nominal, right? So it's both binary and nominal. These groups are not always, with respect to nominal and dichotomous, mutually exclusive. About diagnosis. Oops, I already gave it away. Pushed the button too quick. Also dichotomous and nominal. How about SES? Low, medium, high. Does that have some kind of underlying order or not? Yeah, so it's ordinal variable. Region, rural or urban. Yeah, binary and nominal. And finally, we have race. What do you think about that? Nominal. Yeah, so when you bring me data types as a statistician, I sometimes have to think about this, and sometimes it's not always super obvious what the order is or if there's a lack of order. And we usually have to figure that out through your hypotheses. So depending upon the kind of hypotheses you bring to me, we can sometimes decide if there's some underlying order to these data or not. And that will impact the type of analysis that we end up doing. So, as fellows doing your research projects, most of the time you're going to bring to me some data and you're looking for an association between two or more variables. If you bring me a bunch of continuous data, the types of methods you may see at the simple scale are correlations, scatter plots, maybe linear regression. For categorical variables, you may have contingency tables, chi-square tests, logistic regression, which is a type of what we call generalized linear regression, which you can talk about later if you'd like. Or maybe you come to me with data of both types, and this is probably the most common. You have some continuous data, some categorical data. The methods for these types of data may be box plots, two-sample t-test, ANOVA regression models. But today, of course, we're talking about categorical data, and a big part of categorical data analysis is contingency tables. Also called crosstab tables. So what is a contingency table? These are tables that display relationships between two categorical variables. They're composed of what we call cells, and the cells contain frequency counts of outcomes and exposures for a sample. I'm going to show you a picture of this in a moment. Generally, for contingency table, the rows are your exposure variable, and the columns are your outcome variable. So an exposure is just another word for a risk factor. So if you're doing a regression analysis, you may have multiple risk factors in one outcome. Depending upon study design, you may have multiple outcomes. But in general, when you're doing a contingency table, the rows are your exposure and the columns are your outcome. And here's what one looks like. And specifically what I'm showing you here is a 2x2 contingency table. And these tables are very special. Again, there's whole textbooks written on how to analyze data in a 2x2 table. It seems simple, but there's so many inferences that you can make off of it. And we'll talk about some of those today. In the columns, we have, of course, the outcome, which is often some dichotomous values, present or absent, or dead or alive, or relapse or not relapse. Most of the time in clinical research, the outcome is something negative, and we're trying to model or assess the risk or probability of a negative outcome. In the rows, we have our risk factors. You can call it a risk factor, you can call it an exposure, a predictor, a covariate. There's lots of different words for the variables in the rows, but generally, the epidemiological term is exposed versus unexposed, so I'm using that here. So thinking about the metrics that you can calculate from a 2x2 table, the one that people almost always ask me about is the idea of risk. Risk is the probability of an event occurring in a population. So the simple formula for that is just a proportion. It's the frequency of the event divided by the total population. There's a number of things you can do with risk. If you think back to the 2x2 table we just looked at, we had an exposed group and an unexposed group. So you could theoretically calculate risk in the exposed group and risk in the unexposed group and compare them in some way. Well, how do we compare them? The most obvious one is relative risk. And I'm using these abbreviations here. EER is the experimental event or the exposed event. CER is the control or the unexposed event. So the relative risk is just a ratio of the risk in the exposed group versus the unexposed group. Other ones you may see in the literature that are pretty common, just the risk difference, just a simple difference of the probabilities of risk in each group. One we get asked for quite a bit, especially in clinical trials, is the number needed to treat, which is just 1 divided by the difference. And then finally, this is more interpretive, is the relative risk reduction, which is just the analog of relative risk. It's 1 minus the relative risk. We're going to go into detail about some of these today. I did want to do a quick caveat. I know Dr. Bai talked a little bit about study design yesterday, but I do want to show you can't use risk all the time. And the reason for that is because risk assumes that you have some population that you're studying, and that population is the sample that you're studying is representative of the population. And I'll say more about what that means shortly. But in general, for risk, you can only calculate that in randomized controlled trials. You can only calculate that in cohort studies and cross-sectional studies. So I want to do a quick study design caveat. Again, I know this was presented a little bit yesterday, or maybe more in detail yesterday. I'm doing a little bit today. But the big 3 or 4 studies that you'll see, especially in fellowship or observational type studies, these are surveys, cohort studies, cross-sectional studies, and case controls. The ones I see most in practice, from fellows especially, are cross-sectional studies and case control studies. I do occasionally get a retrospective cohort study, but as you maybe learned yesterday, cohort studies take a long time because you have to observe some exposure and then follow people in time to see if they have some outcome. There's a long latency period there. Prospectively, it could take years to do a cohort study well, and you don't have years for your fellowship. But some people will do a retrospective cohort study, where they'll go back in time. I'm not covering all that today, but we can talk more about that if that's a design that you have interest in. Beyond the observational studies, we have a number of experimental studies like RCTs and non-randomized studies. We have systematic reviews, qualitative research, and animal trials. And what I have on the right is this, what I call hierarchy of scientific evidence triangle. These randomized controlled trials are the strongest single study design that you can do to determine if an exposure or treatment is causal of some outcome. Below the below the experimental group is the observational studies. So I have these ranked, of course, from weakest evidence to highest evidence. So cohort studies are generally the best type of observational studies you can do, but they can be obviously pretty costly and take a long time to carry out appropriately. So again, most of the studies I see from fellows kind of lie in the case control and the cross-sectional area. But with that said, these are all study designs that the core has exposure to, and we can help you with. So now we've kind of thought about this. We've talked about what study designs work for risk. Again, those are randomized controlled trials, cohort studies, and cross-sectional studies. Assuming we have one of those designs, something you can calculate is called the risk difference. And this is a pretty simple calculation. I'm going row-wise in these calculations here. I'm talking about of the exposed, what percent have the outcome? Of the unexposed, what percent have the outcome? It's just simple, a little bit of arithmetic here. So it's A over A plus B, where A plus B is the denominator in your row for the exposed, and C plus D is the denominator in the non-exposed group. To do a risk difference, all you have to do is calculate the proportion in the exposed and subtract the proportion in the unexposed. So again, very simple here, but it's very good inferentially. I did want to make a quick note here that sometimes, depending upon the journal and the, I guess, the hypothesis you want to ask, the 2x2 table could be flipped. You may have the exposure in the columns and the outcome in the rows. And actually, we're going to look at an example where that happens. So this is an old article that we pulled from a while ago, and it's got a control group and it's got a treatment group, ventilation group, APRV, this type of ventilation. And the outcome that we care about that's categorical is 28-day all-cause mortality. And you notice from what I just said a moment ago that the exposure is often in the rows, but in this situation, it's flipped and it's in the columns. So you have to be conscious of that when you're reading your tables. Like, where's the outcome? Where's the exposures? When I'm reading a table, I try to orient myself immediately to like where those things are. To kind of flip it back into our 2x2 design that I've been showing, I have that in the bottom left corner here. We have the APRV intervention group on the top of our table in the bottom left, and then we have the control group on the bottom. To get the risk difference between these groups, we first identify the 28-day all-cause mortality as the outcome, and then we do a simple math here. The control group is going to be 7 over the total, which is 7 plus 19 is 26. So 7 divided by 26 is 26.9% is the risk in the control group. The intervention group risk is 53.8. To do a risk difference, all you do is subtract those two things. And you get the risk difference here is 26.9%. You notice here there's a p-value that corresponds to this, and we get that through what we call a chi-square test. A chi-square test I'll get more to in this presentation, but in general, it's trying to say, is the distribution of the categorical value the same between two exposure groups? You'll notice here that the p-value is 0.089. I don't know how much stats you guys have had, probably some. What would you say about a p-value of 0.089? Any idea? Yeah, I see some heads shaking. In general, that's not significant at the 0.05 level. However, there's more to it than that, I think. I don't like just to look at the p-value and say this is all that we care about. 0.089 is actually, it's pretty close. I may say that there's a marginal statistical difference between the two groups. It's kind of a cop-out in some ways, but we do use that language. What I like more than the p-value is actually the magnitude of the difference. You know, as clinicians, it's not just about statistical significance. It's often about clinical significance. So when you see a risk difference of almost 27%, that can be very clinically meaningful, even though the p-value itself is insignificant. So whenever I'm going through results with young researchers, I try to emphasize that p-value, don't just like scan the document for significant p-values. Also look at the differences and see if the differences are important. And it's not just about 0.05. So just want to say that caveat there. Beyond risk difference, we also consider relative risk. This is another measure that we often calculate. We take the same metrics we had from the risk difference value. We take A over A plus B, which is again just the frequency, divide it by the total population in the exposed. And then we do the same thing for the unexposed, and we just divide those two. So instead of subtracting them, we're now just dividing them. And we create a ratio. And the ratio has a lot of really nice properties that we can interpret. So how do we interpret some of those properties? Generally, we're modeling something that's bad. So in that previous table, we were modeling mortality, which is a bad thing. So if you have a risk ratio that's above 1, that means your probability of mortality is higher in the exposed group versus the unexposed group, or vice versa, depending on how you set it up. If the risk ratio is equal to 1, there's no difference between the two groups. And if the risk ratio is less than 1, we call it protective, or the outcome is better in one group relative to another group. So an example may be a risk ratio of 2. So we'd say the observed risk of having the outcome of interest is 2 times larger in the exposed group relative to the unexposed group. It's kind of generic, So we can do is take it back to our example we've been doing here. And as we said, the nice property about risk is that you can use more like general terms like the probability or the likelihood of something happening is twice as much in one group as the other group. It has really nice like intuitive properties about risk that people like. Going back to our example here, again, kind of resetting this up again, we're looking at mortality. We have APRV and control. The risk ratio is equal to 2. So we do 14 over the denominator, which is 26, and then 7 over the denominator, which is 26, and we get 2. What does that mean? What's this risk ratio mean? Have any idea? Well, we've set it up to where the intervention or the exposed is in the numerator. And we have the unexposed in the denominator. So this tells me that the probability of the outcome is twice as high in the exposed group versus the unexposed group. So 2 times higher. Although I call APRV intervention, that's probably a misnomer because APRV is usually, if you're ventilating someone, they're in pretty bad shape. So they're more likely to die, right? So the probability of them dying if they're having to be ventilated is twice as high than in the control group, according to this example table, which is kind of morbid, but that's what the data show us. So before we move on to the next piece here, I just want to quickly refresh. What designs can we actually use risk? Yes. Oh, yeah. Yeah. Yes, that's correct, because that's a great question. So the way this study was set up, this is just from an old paper we pulled. They clearly have balanced their sample size in some way between the two groups. But if they were not, say like there was 50 in the ventilation group, for instance, you're still calculating the risk as the probability in that group and the risk in the other group, and it's still going to work out the same. I mean, it may not be 2, right? The probabilities may be different, but the calculations are the same. So it's a good question. So I just want to rehash this again, like what designs are appropriate? For risk, we have randomized controlled trials are appropriate, cohort studies, and cross-sectional studies. These are the 3 that we can use risk in. These other analyses, we would not be able to use risk, and I'll talk about that in a second. So the next one you probably come across in the literature, probably even more so than risk, or at least equal, is odds ratios. And odds ratios can sometimes be a little confusing. But in general, all they are the probability of the event occurring divided by the probability of the event not occurring. And we often use odds ratios, as I said earlier, in situations where we don't really have a true sense of the population denominator. In the last example, we were assuming that the 26 and 26 are representative of some population, that it was a sample that was representative of some population. That's not always the case, though. If you're doing a case control study, for instance, you may artificially set the denominators to be equal to each other, or to be in a ratio of 3 to 1 or 2 to 1 or whatever it may be, and you're fixing the prevalence of disease to be something that it may not be in the population. So because of that, a risk does not make sense, if that makes sense. So what we do is instead of using risk, we want to have some other measure of association, and the odds is what makes more analytical sense over risk in these situations. So as I was talking about, it's retrospective study design is typically most frequent for odds, usually case control. And in a case control study, we often start with the disease. We then match controls to the people that have disease and then look back at the risk factors. That's the most common setup for a case control study and the most often used situation for odds ratios. So if you work the math out on this, it actually works out to be pretty simple. If you think about your 2x2 table, it's A over B divided by C over D. So instead of me doing A divided by A plus B, it's just simply A over B in the numerator. In the denominator, instead of C over C plus D, it's just C over D in the denominator. And again, the reason we do that is because the total A plus B is not representative of whatever population you're trying to study. You've artificially set the population in some way, like we talked about. It could be a 2 to 1 or 3 to 1 or whatever it may be. If you do a little bit of arithmetic, in algebra, you can resort this out to be A times D divided by B plus C, or B times C, excuse me. And that's going to be the calculation for the odds ratio. So let's do that. Well, we want one moment. How do we interpret the odds ratio? We interpret it, at least with respect to the numbers, in a very similar fashion to the risk ratio. If it's greater than 1, the exposure is harmful. If it's less than 1, the exposure is protective. The big thing, though, is what I see fellows and residents and even like young statisticians do sometimes is they try to interpret odds in terms of risk, and that's not what we should be doing. We should interpret odds in terms of odds. So if the odds ratio is 3, we say the odds of having the outcome of interest are 3 times larger in the exposed group relative to the odds of having the outcome in the unexposed group. So as long as you keep it in odds and not talk about probabilities with odds ratios, you should be in good shape. As I said, this does not mean you were 3 times more likely to have the event or the outcome. That would be a risk ratio if you talk about likelihood versus odds. Yeah. Well, just think about like what you're doing here, and that's why I was trying to harp on study design a little bit. If your study design, this is the way I think about it. If you start with your exposures and you look forward to the outcomes, like you're not setting the number of outcomes. You're looking forward in time to see who has the number of outcomes. That is when you can fundamentally do risk, because you can say if I have this many exposed and this many unexposed, what's the probability that they experience the outcome? And you did not set the outcome count like you would in a case control. You can do a risk calculation. But if it's an odds ratio is informative when you're going the other direction, when you start with the outcome and you look back at the risk factors, because then you're actually setting the proportion of people that have the outcome in your study. And you cannot calculate risk anymore because you've already predetermined it before the study started. Does that help? Okay. So think about it like that. When you have a case control study, you start with the outcome, you look back at risk factors, you use odds ratios. When you have a cohort study or cross-sectional study, you start with the exposures and you look forward to the outcomes and you can calculate risk. And they're not interpreted the same way. Risk is interpreted as risk, probabilities, likelihood, all that good stuff. Odds are interpreted just as odds. So again, think into our example here. And the truth of the matter is you can calculate odds anytime, but sometimes risk ratios can be more informative. So we do risk ratios. Talk about that more shortly. Thinking about the odds ratios here, how do we do this? Well, the odds ratio, as we talked about with the arithmetic a few minutes ago, we take the number of people in the intervention group that had the outcome, death, 14, and we divide it by the count of those that did not have the event. So it's 14 over 12. That's your odds of the event in the intervention group. The odds of the event in the control group is 7 over 19, and we see our odds ratio is 3.17. So the odds of death are 3.2 times higher for the intervention group. And you see that they're a little bit different here. The risk was 2, the odds ratios were 3. They kind of tell you the same story, that you have a higher risk of dying in the ventilation group, but the way you interpret it is just a touch different. So again, our little triangle, which studies are odds ratios most appropriate? Randomized controlled trials, you can do odds ratios, cohort studies, case control, and cross-sectional. You can do odds ratios anytime, but risk ratios you can only do when you have a representative population where you've not artificially set the number of people that have the outcome. So I've said this a few times now. Relative risk can only be done in RCTs, cross-sectional studies, and cohort studies. Odds ratios can be used anytime, but most frequently you see them in case controls. So this is kind of restating what I just said, but in the example of relative risk is 2.0, where the odds ratios are 3.2. Again, don't confuse risk and odds. So I want to do a little poll question, do like a real world example. So read this for a moment and think about it to yourselves, and then we're going to go over a couple questions together about this example. So take like a minute and think about this. Think about the design. So we have cross-sectional studies versus cohort studies versus case controls. Think about those 3 observational designs. Think about what metric we would use, odds ratio versus relative risk, and think about how we'd interpret that. Good to move on to the next slide. All right. So what do we think the study design is? Also put RCT on there. I can go back and forth a little bit if we need to. But what was the study design? Remember with cohort studies, you start with the exposure and you look forward to the outcomes in time. When I say you look forward, you look temporally forward. Cross-sectional is just one slice in time. Case control study, you start with the outcomes, you look back at risk factors. And RCT, you randomize the exposure. So let's click back on that. Let's see. I would think of this as like, what do we do? In a case control study, I would have went through my sample, and maybe I could have made the wording a little bit clearer in this. I would have went through and figured out how many people had chickenpox and how many people did not have chickenpox, and then look back in time to see if they were vaccinated or not. That's a case control. A cohort study would start with who was vaccinated and who was not vaccinated, and then follow them in time, which again, maybe I should have said that a little clearer, to see if they got chickenpox or not. Cross-sectional study would have simply said, at one slice in time, what percentage had chickenpox versus not, what percentage of those were vaccinated versus not. It's all just like one snippet in time. So that's, broadly speaking, what the design differences are. My intention for this question, maybe I'll make it better for next year, just give me a new one, was we're thinking about cohort studies here, where we start, oh, go ahead. Yeah, so the outcome would be the individuals that got chickenpox, right? Yeah, and maybe if there's an outbreak, you're like trying to go through and you're trying to say, well, I guess it depends, you're right. If it's an outbreak study, you're going through and you're just sampling people to see who have chickenpox. I could see it in that way. And then you kind of look back. And these are great questions, because like when you come to me as a statistician, these are the kind of things we can talk through and like think about like the directionality of the data collection. That's really important too. You know, how are you getting your data? Are you starting with people that have disease versus not disease, and then all of that? But in general, this type of study, and what my intention was with this question was we'd start with vaccinated versus not, and then see what percentage of those actually got chickenpox. So that would be a cohort study. So bearing with me in that way, what measure of association is most appropriate in a cohort study? Yeah, risk ratio. If you have that table to reference, how would we calculate that? Well, it'd be the number of people that got chickenpox in the vaccinated group over the number of people that got chickenpox in the unvaccinated group. And what you can see here is the probability of getting chickenpox in the vaccinated group is 12%, and it's 43% in the unvaccinated group. So what you do is you just divide those percentages by each other, and you get 0.28, and that is our risk ratio. So like, what does that mean? That's a funky one. People usually like to interpret risk ratios above 1. So what does a risk ratio below 1 mean? Any idea? It is protective. That's correct. How would I put this? Anybody know how to put this into a sentence? I like to use the relative risk reduction. We showed the format. It's 1 minus relative risk. So you could say the risk of being diagnosed with chickenpox is 72% lower in the vaccinated group relative to the unvaccinated group. So it's 1 minus 0.28. That's what's called the relative risk reduction. The reason I showed this example like this is because people, you know, including myself early on, struggled sometimes thinking about it in the other direction. So it's helpful to think about, you know, how, if depending upon the directionality of the association. That's what I'm getting at here. So in summary, for a 2x2 table, some of the measures we can calculate are chi-squares, risk differences, risk ratios, odds ratios. These are all very, very common. You'll see them throughout the literature. While the direction of the effect sizes can be interpreted similarly, like we saw odds ratios and risk ratios, both told us that there was a meaningful difference between the exposed and unexposed group in our example. The actual interpretations are a little bit different. So keep it risk versus odds. Keep those two things separate in your head. And as we talked about, risk ratios are fundamentally not appropriate for case control studies, but you can use odds ratios anytime. Yes? I do not have that in the talk today, but I can give you some material if you'd like to have that. Absolutely. You're right. You're right. So significant, that goes a little bit back to, you're right. Some measure variability around those estimates is critical. And the confidence interval should correspond to a p-value. So we are talking a little about p-values today. But when you have smaller samples, your confidence intervals are wider. And there's methods you can use to account for that in categorical data analysis. Usually exact type methods are pretty popular. But in general, you know, if it crosses, if you're doing like a risk difference, if a confidence interval crosses 0, that would indicate an insignificant risk difference. And then for risk ratios and odds ratios and all that, your marker is 1, as we talked about. If, you know, as I was talking about earlier, I think the big thing is to think about clinically meaningful differences as well. You know, a p-value should correspond to a confidence interval, and smaller sample sizes are going to give you wider confidence intervals, which may indicate to you statistically insignificant findings. When in reality, it's the difference that I think is equally important, and you can determine, like, is that difference meaningful clinically, as opposed to just, is it a p-value or is the confidence interval crossing 0 or 1? Is that helpful at all? Yep. Yeah. Not significant, not a statistically significant odds ratio, right? Yes, that is a forest plot. You see those a lot in meta-analyses, and you also see those a lot in multivariate logistic regression analysis, or multinomial, whatever you're doing. And you're right, it kind of gives you a quick summary of what bivariable relationships are significant at the 95% level. But even so, I think about ratios in themselves are effect sizes. And even, and you mentioned a small sample size, which I appreciate because this happens a lot, especially in pediatric research, where we're dealing with pretty rare diseases. And, you know, you may get an odds ratio of 2, 2.5, 3, you know, what I would consider very large or moderate to large effects. But with a super small sample, your confidence interval may still cross 1. And you're kind of like, well, shoot, what do I do? What I often tell investigators, again, is that, like, report out that this effect size is very large. Like, and a 3 is very meaningful. It's like a 3-fold change of using a risk ratio, for instance, in one group versus another group. I think that's very important to report out in a manuscript. And, you know, you may get a reviewer that writes about, oh, it's greater than 0.05, but if anything, you know, it can be a primer to get a bigger sample. I mean, most of the time, these studies are exploratory or pilot, especially in rare diseases. And it's going to take some type of, like, bigger initiative, like a consortium or something, to really get a big enough sample to do that with good power. So that's a whole nother talk about statistical power. But it is something to think about, and things that we can help you work through if you're stuck. So that's a good point, though. Next year I can add in some confidence interval stuff. I'll do that. Beyond the 2x2 table, something else you'll see. Not everything is a 2x2 comparison. Another one, it's an extension of the 2x2 table, which we call an I by J contingency table. I represents the number of rows, which is often the exposures we talked about, and J represents the number of columns, which is our outcome. And what I have at the top here is typically how you as clinicians hand me data, right? You have the ID on the left side, you then have some therapy, and then some outcome. And it's possible that either in the levels of the therapy value or the outcome value, that it's not just a simple 2x2 table. So what I give down here is a classical example of placebo versus aspirin. I know that this is now being a little bit contentious. There's some new data that show this may not be the case, but it's been long said that aspirin helped certain groups of people prevent heart attack, and this is some of the original data from the 80s. But what kind of table is this? This is not a 2x2 table. Think about the number of rows and the number of columns. What would I call this? Any idea? That's right. Thank you. I wasn't sure if I was asking that question in the right way. So that makes sense. Yeah, it's a 2x3 contingency table where you have 2 groups for the exposure and 3 groups, and 3 groups for the outcome. So what do I do with this table? How do I ask and answer questions with it? You as a researcher may ask me the question, is there any association between taking aspirin and the risk of heart attack? What I would do first off is just calculate the simple summary statistics. It shows here if you collapse the fatal and non-fatal heart attack groups, because they're both pretty rare, we can see that in placebo patients, almost 2%, 1.7% experienced some heart attack, and in aspirin patients, less than 1% experienced heart attack. So is this difference meaningful? Is it significant? These are all questions that we get asked pretty frequently as statisticians. Well, what I like to do when you come to me with these questions is really try to frame it first as a research hypothesis. So when I say research hypothesis, what I mean is I want you to propose to me maybe a direction of the relationship. So use of aspirin will decrease the incidence of heart attacks in adults with coronary artery disease. That helps me know as a statistician what direction I should be testing and how I should be thinking about your research question. What I typically do on my end, once you give me your research hypothesis, is I convert it into a statistical hypothesis. And you may have seen some of these in your intro to stats class. Again, I'm letting P here be the combined heart attack proportion. The null hypothesis may be that there's no difference between placebo and aspirin. The alternative it depends upon our conversation. It could be one directional, where the placebo is better or worse than aspirin, or it could be bidirectional, where placebo and aspirin are just different from each other. Most of the time, we're testing that bottom one. The placebo and aspirin are different from each other, unless you are specifically looking at a one-directional hypothesis, usually in a clinical trial setting. So if you were to bring me this type of data where we have a 2x3 table, they're both categorical variables, what type of inferential test or statistic do you think I would do with this data? Any idea? I think I heard somebody say it. It's chi-square test of independence. So chi-square tests are very common. Anytime you hand me a bunch of categorical data, I'm going to give you back a bunch of categorical p-values with chi-square tests. I shouldn't say anytime, but a lot of the time. Chi-square statistics test where the distributions of categorical variables are different from each other. They're calculated from what we call observed and expected values. And these expected values come from marginal sums, which I'll show you in a moment with the tables. We then, from those expected values, calculate a chi-square value and get a degree of freedom and then derive our p-value. So I thought it may be a little fun here to show kind of like what we do on the back end. Of course, we're not doing this by hand, our software does it, but we did do it by hand in undergrad, maybe grad school. So say you gave me this table and you wanted to know, are these two groups different from each other? What the software that we work with does first is it calculates expected counts. And I'm using this example right here to give you an idea of like what it's going to do. So I want to get an expected count for each cell in this 2x3 table. It uses, say I want to calculate the expected count for that top left cell, the fatal heart attack in the placebo group. To do that, I need these three values. I need the marginal total for the fatal heart attack group. I need the marginal total for the placebo group, and I need the denominator for the entire sample. And you can see here, using this formula, 23 times 11,034, which are the marginal totals, and divide that by 22,071, that's the expected count. So 11.5 would be the expected fatal heart attack count. And again, the null hypothesis, and this is important, the null hypothesis is that there's no difference between the groups. So this is the expected count if indeed there was no difference between the groups and we had these totals around the table. I then use our little formula from the previous page, which is the observed minus expected squared over the expected, and I calculate a chi-square value for each cell. So 3.68 is the chi-square statistic for the fatal heart attack placebo cell. I then sum those things up, get my degree of freedom, and I calculate a p-value. So this p-value here is very, very significant, 0.001, less than 0.001. What do we conclude about this difference? Is it significant? Well, it is significant. But what I want to emphasize about this, and this kind of goes back to the question about confidence intervals. If you think about the sample size here, it's humongous, right? It's like 22,071. It's a large cohort study that was following people for years and years. In reality, heart attack's a pretty rare thing in both groups, right? It was like 1.7% one group, 0.9% in the other group. Which clinically may not be that meaningful, right? It's like 0.8% different between the two groups. But our p-value is super significant. So again, it kind of goes back to when you have a super big sample like this, your confidence intervals are going to be very, very tight. And in this situation, that confidence interval will not cross 0. So because of that, we get a super significant p-value. But I want you again to think about clinical meaningfulness here. Is a 0.8% difference between these two groups over 22,000 people something that where you got to run out and tell everybody to take aspirin? Maybe, maybe not, right? That's kind of where it gets to be like the clinical inference versus the statistical inference. So whenever I'm working with investigators, in addition to p-values, whenever I have really big samples and really, really small samples, in addition to p-values, in addition to confidence intervals, I often give some metric for effect size. And in this situation, the effect size may be considered pretty small. There's not that big of a difference between them, although our significant p-value was very, very, very small. So just want you to keep that in mind as investigators, that we shouldn't always just run to the hills and scream when the p-value is significant. We got to think about the broader clinical implications. So the last slide I have here is just a simple slide summary of some of the tests you may hear us run for categorical data. You'll see the most prominent one here is the chi-square test of independence. If the data are nominal or dichotomous, you can almost always just run a chi-square test, or if the sample sizes are too small, you may run a Fisher's exact test. The statistician can help you with that. If your data are ordered, some of these new tests kind of come in here, and most of these tests kind of revolve around trend. When you have ordered data, there's some underlying trend that you're typically trying to analyze there. So the Cochrane-Armitage test of trend is very common. Cochrane-Mantel-Hansel statistics are pretty common. If you have two ordered variables, you may see Spearman correlations and Kendall's correlations. But the point of this table is that the data types matter and your research questions matter. What's the exposure versus what the outcome matters, and then how those data are comprised matter. And that will inform a statistician of what type of tests they need to run for your data. In addition to these more simple tests, there's all kinds of regression models that we did not have time to cover today. Again, these can be a whole semesters, but binary logistic regression is very common, ordinal logistic regression, multinomial. So binary is obviously a dichotomous outcome, ordinal is an ordinal outcome, multinomial is a nominal outcome. And they all use different tweaks on the same generalized function to get you some odds ratio estimates. There's other situations you may run into. If your categorical data are paired, you may consider McNemar's tests. Or if you're trying to find agreement in some categorical data, you may have kappa and weighted kappa statistics. There's other things like sensitivity and specificity. There's so much in categorical data that we didn't really have a ton of time to cover today. But what I wanted to do was give you some exposure to the most common types of descriptive and basic inferential analyses that we run for categorical data. So hope you got something out of that. But in general, you have a wonderful resource here in the biostats core. And we've helped all kinds of projects over the years with different types of data, whether it be categorical, continuous, whatever it may be. So if you have questions about it, please come to us. So that's what I have today. I think we have some time for 5 minutes for questions or so. Do you have any questions?
Director said, oh, just sign that check over as so many of the fellows have been working on their research project.
Yeah.
Could you talk about generality versus specifics, about sort of some of the lessons learned about best practices, collecting data or working with different work?
Yeah, I would say the biggest things come to us pretty early in your research process. If you've worked with your mentor, you figured out broadly like what a good research question is. We can help you refine that. And what often, like I've reviewed these grants too. And what often happens is, and they're largely very good. But what I often see in these grants is that the aims can be ambiguous with respect to your outcomes, with respect to your exposures, your sample size. Sometimes it doesn't seem feasible. So, statisticians help you think through these things and think through like what is a proper design in your time window that makes sense given the data you may or may not have access to. Are you trying to do a prospective study? We can help you work out a power calculation so you can figure out how many people you need to approach for a prospective study. If it's a retrospective study, we can say how many charts that you probably need to pull or review. We can help you really delineate pretty well about what type of analyses make sense to answer your questions most appropriately. And the later you come to us, the more stuff kind of gets baked in and the less we can help you. So, I say come to us early, and that's always a very good start. With respect to data collection and good practices around that, I think that partially revolves around our conversation. Like I said, a power calculation can help. So you only need like 30 people here to detect a moderate effect or something, or maybe it's exploratory. There's so many questions and there's so much variability in what you could ask us. But we can help you think about your data elements. We can help you think about, ways to collect your outcomes better, maybe ways to ask questions of people better, if it's prospective, for instance. So, that's probably the biggest answer is like, just come to us sooner, and we can put you on the right track towards data collection. You have options, right? A lot of people use REDCap if it's prospective, even retrospective if it's like a small amount of cases that you are querying, maybe from Epic. You can put that into a REDCap to keep it clean. Some people do bigger, like registry type studies, and they have to query tens of thousands of records, and you can't put all that into REDCap. So how do we keep that clean and keep it standardized for the statistician? So, and you can go to our website as well. We have some rules not rules, but we have some guidance on our website for how to format your data for us to help facilitate analysis as well. So that should be out there.
So you don't do the REDCap, but you can advise on all those kinds of things.
Yeah.
Dr. Weiss shared with us yesterday through a questionnaire a script of what you can do with when people come to you and how it actually directly translates to a paper. And so it really through. And I think that the other thing you can talk about how to contact you and what
Yeah, it's a good question. So you can go to our website, and I just Google pediatric biostats core Emory, and we're the first thing that comes up. So you have some free time with us. So through partnership with Children's and Emory, we will help support your at least the early phases of your study at no cost. So we give. It's 4 hours on the website, but practically speaking, we usually don't nickel and dime. And give you a few hours beyond that if needed. But we help you think through like the design and like the best way to collect your data and kind of get it off on a good start. I will say, from the beginning of a project through the very end, it's going to take more than the free subsidy hours. So that's why, applying for different grants and maybe speaking to your mentors is important. The average fellows project will probably take from our first discussion through publication, 30, 35 hours of biostats time. And you, practically speaking, have around 4 to 6 of free time. So we have to cover the gap somewhere. So that is something to be thinking about. Again, we don't want to be a barrier to your work, and we'll do all we can to support it. But that is something to have. That's a conversation that we'll have early on. Is like, what is the funding mechanism, or how can we help you find funding? That's it too. We work with you on these grants. So like, if you're applying for a Warshaw or whatever your mechanism is, we will help you write up a stats section. We'll help you think through all of the specifics of it. So we want to facilitate your research, not be a barrier to it.